Imagine the universe as an ocean you can't step out of. Not a surface you sit on, but a deep, continuous ocean of space-time that flows everywhere. Planets, stars, spacecraft, even light are all embedded inside it. Here's the twist. Nothing just sits on space-time. Massive objects are dynamically woven into its curves. Their mass grabs the grid, tugging it into waves and currents. That grip provides both resistance and guidance, the secret sauce of orbital stability. Near a planet, the ocean is rough, strong curvature, strong coupling. Far away, it's calm, low curvature, weak coupling. In the field decoupled trajectory model, FDTM, the key parameter is the coupling coefficient. Let's call it K. K measures how much you feel the ocean. High K, you're strongly embedded, like a planet. The curved grid lines become waves steering your path, and the ocean pushes back enough to keep orbits locked in. Low K, you're more like a small boat in calm water, a nimble spacecraft gliding through low-density space-time, shaping its own path with minimal interaction. Think of a planet as an island that makes currents. Those currents don't just pull, they guide. A spacecraft can choose routes that skim along quieter channels, decoupling from the rough stuff while still living inside the same ocean. So, curved grid lines equal waves, planets equal islands, spacecraft equal boats threading the calm. One ocean, different ways of feeling it. Paper ready, it sounds like this. In FDTM, all matter and energy are embedded within an ocean of spacetime. Masses create localized deformations that guide motion and generate effective resistance, while low-mass bodies traverse calmer regions with minimal interaction. The coupling coefficient K parameterizes this interaction, unifying stable, strongly coupled orbits with decoupled trajectories, within the same continuous manifold. We don't leave the ocean. We learn how to swim in it.
Imagine space not as empty chaos, but as a calm lane between storms, a quiet highway threading the gravity of planets and stars. I call it the midfield corridor, where space-time is as smooth as it gets between massive bodies. Here's the picture. Big objects, stars, planets, black holes, dense space-time, carving steep valleys and hills. Between them, there's a gentle stretch, a valley floor that's almost flat compared to the nearby pits. That's the midfield corridor. In this lane, mass-induced curvature drops, geodesics straighten, and the universe feels less sticky. Think of motion here like gliding above a calm ocean. Near planets, the water chops and tugs. Your path keeps bending. In the corridor, the chop fades. Your craft couples less to the local space-time distortions, so resistance to staying straight and fast goes down. Now zoom in, way in. The vacuum isn't truly empty. It seethes with virtual particles and fields flickering in and out. In this quarter, that froth thins to a low-density hush, sparsely distributed Higgs interactions, fewer virtual flickers per patch, like air getting thinner at high altitude. The effective coupling coefficient, the stickiness between matter and the space-time grid, stays low. Fewer nudges, fewer drags, so navigation flips. Instead of slingshotting from one gravity well to the next, I chart routes along gradients of lowest curvature, ribbons that already exist between worlds. It's not warp, it's not magic, it's picking the smoothest asphalt on a cosmic road trip. What does this buy me? Efficiency at high speed, less course correction, more predictable trajectories, corridors naturally align between bodies, sun to Jupiter, star to star, like invisible rail lines if you know where to look. If I had to say it paper clean, the midfield corridor between massive celestial bodies represents a region of minimal space-time curvature and subatomic particle density. Within this corridor, the effective coupling of matter to the spacetime grid is greatly reduced, producing a natural low-resistance pathway. Spacecraft can exploit these corridors to traverse interplanetary or interstellar distances while remaining embedded in the same continuous spacetime manifold, but without the substantial resistance experienced near high-mass objects. Calm lane, long reach, floor it, smart.